Last one. This one is the most challenging, but just because I'm having you recall back to chapter 3 when we were doing DAT-VV. It's still just a forces problem. You have to get your acceleration from doing DAT-VV. I'm making you use the favorite equation. There's no time given to you. Hint, hint. Okay. Here's the free body diagram. We've got an object on an inclined plane. This is a sled on a hill, and the slope is 32 degrees. So far we've talked about how that tells me that the angle inside here is 32 degrees, and if you can show me how to do that, you get extra credit. Before Thanksgiving, it's due. Okay, so on here, we know that, as always, sum of the forces in the y direction, that's neutral, or equilibrium. So we've got my normal force, upward, plus my force due to gravity in the y direction. That's all equal to 0 newtons, because that's all balanced. Not necessarily the case, well, definitely not the case, for the object in the x direction. So we're giving him we're giving the toboggan an initial speed of 6.0 meters per second. And as it goes up the hill, it's going to go a certain distance. And what you're trying to solve for in number 6 is that distance. So we're going to take the acceleration that we're solving for using our force problem and plugging that into the DAT-VV equation. So the DAT-VV is actually coming last here. So if that's a little hint for you, it comes last. In some of our other problems, we've had to do DAT-VV, solve for an acceleration, and then use that acceleration in a force problem. I'm going a little bit backwards. We're doing a force problem to get an acceleration and then put it into DAT-VV. So how we're going to find our acceleration is knowing that the sum of the forces in the x direction are equal to mass times acceleration in the x direction. Same equation that we can use every single time. I know that the sum of the forces in my x direction, well, one force is my force due to gravity in the x direction. And the other one is going to be my force due to friction. Now, I've actually drawn an error on here. The problem is, if the toboggan has a velocity going upward, is the friction going to also act in that same direction? No, it's not. So, I actually need to redraw this. Force of friction is acting downward. Here is a very, very important thing, something that I feared would definitely trip some people up. If this vector is acting this direction, is it going in the positive x or negative x direction? Remember that we've taken our xy plane and we've just tilted it. Positive x is down the hill, negative x is up the hill, negative y is down into the hill itself, and positive y is straight up perpendicular from the hill. That means that this friction is actually acting in the positive x direction. So when you're putting these two together, please notice that the force of gravity and the force of friction are both acting against the sled to try to slow it down. So these two things are actually both positive. They're not canceling each other out, they're actually helping each other. That's going to make the rate of slowing down, the rate of deceleration, negative acceleration, greater. So once you find those, if you add this all up, divide by the mass, you're going to get that overall acceleration in the x direction. I hope that's useful. I think that's all I need to give you. I think you're going to be okay. Okay, on the back side, there's another mixture of problems. Some of them are the easier ones where we're talking about things on a flat plane. We're talking about some very basic problems. There's a mixture in there. I think you guys can handle all of them. I'm sure some of them are going to be a little tricky, but really try to give yourself a little bit more credit. You guys do a really good job in class of figuring these problems out, and I think that you're going to be okay. So work together. It'll be fine. Have a good day.